All right, so remember last time we were talking about what happens when you put a charge next to a conducting plate. So this was a discussion about the method of images. And I'm just going to briefly fly through the remainder of that discussion so then we can proceed. If you do have more curious, if you are curious about more, go make sure that you check the textbook. It has a lot more details there. So we ended last time saying that if you have a conductor and a charge next to it, the electric field lines coming from that charge look exactly like half of the electric field lines coming from a dipole. And I said that this wasn't that this is not just a similarity, it is an exact relationship. And so the question is, and so I made that claim, and you could prove that claim. It takes a bit of effort to do so, but you can prove it. I'm not going to. But the reason I brought this up is because you can use this equivalence of fields to solve complicated problem using the tools of just 2-point charges. So the question is how do we do this? So the way that we would do this in principle is we just replace the flat conductor with the imaginary image charge. So all you do is you look at your problem with the conductor and you just say, nope, there's no conductor there. There's just another charge on the other side. And then you remove the conductor. And then you solve the same problem. So after doing so, the system might look like this. You have a dotted line where the conductor used to be. You have your real charge with, say, charge plus Q. And maybe this distance here is, that's not a straight line at all. Maybe this distance here is A. So then you'd put an imaginary charge the same distance A away with a minus sign, also known as the image charge. And so we can use this trick to find the force on the real charge from the conductor. And the reason we can do that is because the force would be precisely the same as the force on the real charge from the negative charge, from the image charge. So it does have to be a flat conductor for this to work. So the force on the real charge from the image charge is the same as the force on the real charge by the conductor. And so we can just do that computation with just two charges, and we get that this is 1 over 4 pi epsilon naught q squared over 2a quantity squared, which is just q squared over 16 pi epsilon naught a squared. Does that dotted, yeah, so that dotted line represents where the conductor was. And so that just is the force on the conductor, sorry, on the charge from the conductor. And so you might ask why the charge feels a force from the conductor when the conductor is in principle neutral. And the way to think about that is just that if you put a charge near a conductor, the free charges in the conductor are going to rearrange themselves so that the electric field enters perpendicularly to it. And so what will happen is you'll get a clustering of opposite signed charges on the surface of the conductor. And so what's really attracting the real charge is the increased density of the surface charges on the surface of the conductor. So you can also, in principle, apply this method to multiple charges on one side of a conductor by superposition, right? So instead of just having one charge near a conductor, you can have a whole bunch of charges wherever you want, right? And then the point is all you would have to do is just introduce a single image charge for every single charge on the real side of the conductor. And so you could see how this generalizes. You could even do a charge distribution near a conductor. You could say have a ring of charges near a conductor, and there would be an image ring of charges on the other side. And so you could compute forces for more complicated things. And I believe an example like that is actually worked out in the, it's either worked out in the textbook or in the other textbook, the one that I sometimes link to. Yeah, and I'll let you know what those, I'll let you know about those examples after we finish with image charges. So I did just mention that the surface of the conductor attracts the real charge by accumulating some negative charge on its surface, right? And so you might wonder, how does that charge distribution behave? I.e., we know that the negative charges will be attracted to the center of the conductor. So like there would be more negative charges here, and there'd be less probably further away. The question is exactly how do we describe that mathematically? Oh boy. And we can use this method of images to do that, to solve that problem, to figure out what the charge distribution is on the conductor when a real charge is near it. So let's talk about that. Let's actually go through and work out that example. So this is on the surface, by the way. So what we're going to do is we're going to use Gauss's law and the method of images to figure out how the charges distribute on the surface of the conductor. The method of images, by the way, is just this idea that you can replace a conductor with image charges, and it's identical. Remember, sigma is the surface charge density, so it's how the charges distribute themselves on the surface of the conductor. So first of all, we know that on a conductor, or we know from Gauss's law anyway, go back and look at lecture notes from, I think, Thursday. Yeah, I think it's from Thursday. So on a conductor, we know what the electric field is in terms of its surface charge density. So I'm going to write this in a slightly different way. So say here's our surface of our conductor. Maybe this direction is the x-axis, this direction is the y-axis. And maybe you could imagine drawing a circle on there in the xy plane that has radius r. So from Gauss's law, we established that the magnitude of the electric field as a function of position on the conductor, so this is our conductor here, just viewed from a slightly off angle, that's equal to the surface charge density at that position divided by epsilon naught. Now, just as a quick note, this assumes that the charge distribution on, you know what, let me actually put absolute values around here. That'll be more correct. So this tells us the magnitude in terms of the magnitude of the surface charge density. So we at this point, we know how to find the electric field somewhere on the conductor. All we have to do is we just use the method of images to find that. So we want to find sigma of x and y, i.e. how many charges are there at a given place, or sigma of, say, r, if it has cylindrical symmetry. Sigma is surface charge density. Remember that, we're going to use it for the remainder of this course. So we want to find what sigma is, the surface charge density on the conductor. So we need the electric field everywhere on the conductor. just something like, if we can use this relationship, we can use Gauss's law to relate the electric field to the surface charge density, but we need one of them to get the other. And so the way we do that is we use the method of images. So I'm going to draw a picture with the, that's a sigma. Sorry. We're going to use the method of images with an image charge rather than the conductor to find the electric field everywhere on the surface. So what I'm going to do is I'm going to draw a dotted line where the conductor would have been. I'm going to draw our real charge. We're assuming, by the way, that there's just a single real charge. But again, this can be solved using superposition. So the sigma that you would get from a real charge, from a single real charge, you just add up the sigmas at any given place from all of the charges. Right? So we have a plus q here, say. And so the method of images would suggest this distance is a, this distance is also a, that we should put an image charge with charge minus q on the other side of the the other side of the conductor. So let's say we're interested in the electric field at, say, this point. We want to know what the magnitude is at this point. Now I'm going to call that E of r. And the reason why I'm doing that is because you should be able to see that it doesn't matter. We're trying to find the conductor. We're trying to find the charge distribution on the conductor. That's what we're trying to do. We want to find sigma of x and y. So if you put a charge near a conductor, how do the charges rearrange themselves on the surface of the conductor? That's a thing we know happens. We just don't know how it happens precisely, like what the formula is for where those charges are. So we're trying to do that. So imagine that the charge is placed somewhere. It doesn't really matter what x and y are to figure out where the charges are. All it matters is the distance, like the perpendicular distance from the charge. Yeah, it's the radial symmetry that lets us do this. So we don't have to write it in terms of x and y. We can just look at it in terms of the radial distance r. So the picture is like this. And so it doesn't matter which side you're on, right? It's still r. So we can just write the electric field in terms of the radial distance on the surface of the conductor rather than using x and y. We're not assuming that there's radial symmetry. There is radial symmetry here, right? There has to be, because the point charge doesn't care how you rotate it, and neither does the conductor. Anyway, so the electric field from plus q at this point, drawing a dotted line, would be in this direction. Come on, that'd be, say, E plus. The electric field from minus q would be, say, in this direction with the same magnitude because of the same distance away, just in a different direction. This would be E minus. And so the total electric field would be the sum of those two things, right? And so that electric field would just point to the left, and it would have a magnitude, which is given by whatever it's given by. So the whole point of this, and what I kind of just explained in words, is that by symmetry, like you can flip across the horizontal axis, we have that the magnitudes of the electric fields from each charge are equal. And further, we also have that the electric field from the positive charge, that's just equal to the magnitude of this as a function of distance. Sorry, as a function of r. This r, by the way, does not mean distance. It means the perpendicular distance, as it were. This would just be effectively kq over r squared, right? But we're going to use 1 over 4 pi epsilon naught. So this is 1 over 4 pi epsilon naught times q. And then what's the distance? This distance here is the square root of r squared plus a squared. And so when we square that, we would just get a squared plus r squared in the denominator. So that's the magnitude of the electric field from just the positive charge. Then we have to do a little bit of geometry to find the magnitude of the electric field, the total electric field. This just involves drawing some triangles. It works out that you get that it's twice the electric field from the positive charge times the cosine of the angle theta, where this is that angle theta. And so that geometry would tell us, or the trig, I suppose, would tell us that cosine of theta is a over square root a squared plus r squared. And so at the end of the day, by the way, all of this sort of thing you've done before, so that's why I'm going over it quickly. the magnitude of the total electric field, the one that points to the left, is just Q times A. And there's a bit of work going into this. I've done simplification. Divided by 2 pi epsilon naught times A squared plus R squared to the 3/2. So you can see that the A in the numerator is that A. There's an extra factor of A squared plus R squared to the 1/2 in the denominator. There's 2 factors of A squared plus R squared in the denominator from that denominator there, and then there's a factor of 2 that makes that 4 become a 2. That's where this comes from. And so that is the electric field at a given distance from the center. And so what we can find using Gauss's law, using our relationship we derived from Gauss's law up here, we can find that the charge density at a given distance from the center on the conductor is Q over, or QA over 2 pi A squared plus R squared to the 3/2. And I'm actually going to put a minus sign in front of here. And the reason why I'm going to do that is because we know the electric field lines are supposed to go into the conductor, right? The electric field lines should be pointing into the conductor because they're coming out of the positive charge. And so the only way to have the electric field lines go into the conductor would be to have a negative charge distribution. That also kind of makes sense. You have the positive charge on the outside of the conductor will attract the negative charges inside the conductor, so they'll get closer. And so that's why we have a negative sign here. So I'm just going to write the negative sign is put in by hand. We could have not put the negative sign in by hand, but that would have involved being a lot more, not rigorous, but a lot more precise with the coordinates that we're using and things like that. And we would have had to write the electric field as a vector rather than just as a magnitude and so on. So that's why I ignored that. Okay, so that is the amount of charge that is at a given position, or that's the charge density. So then the question is how much total charge is polarized? Like initially the conductor is neutral, but then some of those charges get pulled over to the edge. So the electric field from a positive charge points away from the positive charge. The electric field from a negative charge points towards the negative charge. So I just drew those in those directions. So the question is how much total charge is yoinked from the neutral atoms and distributed on the surface of the conductor? And we can find that just by integrating. So the charge on the surface, the total charge, and it's smeared out throughout the entire surface, would be equal to an integral of sigma dA, where you're integrating over the surface of the conductor. And so we can just use polar coordinates since that's the natural coordinate system associated with our charge density. So we're just going to integrate over the entire plane. And so it's just an integral of sigma of r, and then the surface element in polar coordinates is r dr d theta. And so you can actually just do this integral. It's not super challenging to do, but takes a bit of effort. You have to do a substitution, some stuff like that. But at the end of the day, what you end up with is that the total charge that's been polarized on the conductor is negative Q, which is good because that's exactly what you would expect to happen. You wouldn't expect more negative charge to accumulate because what's trying to happen, or what's effectively happening, is you have the positive charge will pull as much charge as needed to create the field that produces the field that you get from the method of images. So really what's happening in this method of images is you're taking this negative charge and you're just smearing it out on the, that's terrible, you're smearing it out on the surface of the charge, of the, smearing it out on the surface of the conductor. And so the method of images really just says you can actually just treat all of that smeared out charge as just a single charge at a different place. And that's basically why this works and why it's not surprising that you get minus Q. So I put the negative sign in by hand, basically because we know for an infinite plane of charge, the field lines go out if the charge is positive. and the field lines go in if the charge is negative. And so we needed to make sure that this whole thing was negative because we know the field lines go in. Right, the smear is across the whole infinite surface. Is the upper bound on the inside triangle infinity? Yes, it is. Yeah. On the inside integral. Yeah. And that's because we're integrating over the entire plane. All right. So we could have solved this question differently using Gauss's law, and there's that's done in the LibreText textbook in section 1.8. There's also a discussion of the electric field on the other side of the conductor, which is also near the end of section 1.8. Basically, almost all of this is in section 1.8. But there is a good example which computes which does this sort of thing for a ring of charge near a conducting plane, and that's example 8.1 or 1.8.1. This is a ring of charge near a conductor. Section 1.8, example 1.8.1. Rho didn't show up anywhere. And we have a lot to go over. So keep that question and we can talk about it after lecture. All right, we're going to completely change gears now, kind of. We're going to talk about the potential energy of charges. So for those who are following along, we are done with chapter 1 now in the LibreText. Right, so first, I want you guys to think back to our discussion about dipoles. When we talked about the energy of a dipole, we had to compute the work done on the charge to find the potential energy of that dipole. So just as a quick reminder of what of the work done on a charge, in some electric field, that would just be an integral from A to B, and where A and B are just some points in space, of the force dotted into the path, whatever that path that the charge takes. And so you could write this as an integral from A to B of, well, the force is just the charge times the electric field dotted into whatever that path is, maybe dx I hat plus dy j hat plus dz k hat, right? That path will go throughout space and that will be determined by whatever it's determined by. And so in the example that we gave, when we were talking about dipoles, this just worked out to be q times e times dx because the electric field was just in the x direction and the path that it was moving in, well, it doesn't really matter because because the dot product would just make the x component drop out since the electric field was proportional to, the electric field was just in the x direction. And so we ended up with, in the previous example, after a little bit of work, we got that the work done on that charge was just the charge times the magnitude of the electric field times delta L, which was the distance that the charge traveled. And then we said, oh, hey, well, we can just write the work done as the negative change in a potential energy. So the change in potential energy of that charge, UB minus UA, was the negative of the work done. And that was just minus QE delta L. So we did all of that like in the second lecture of this quarter, I think. Maybe the third lecture, something like that. And that's great. Like that's all fine and dandy. If you know what the electric field is, it's easy to find the potential energy of a charge in that field. But that's not usually what we have. Usually we have some configuration of charges and we want to find the potential energy of that configuration. So let's talk about the potential energy of 2-point charges. It's the simplest example. We have 2-point charges. What is the potential energy of that configuration? This would be like, by the way, asking what's the potential energy of, say, the Earth and the Moon, right? You have two things that gravitationally attract each other. There's some potential energy associated with that gravitational attraction. We're asking what's the potential energy associated with the electrostatic force between two charges. So let's say that the initial configuration of our system is we have 2-point charges, Q1 and Q2, separated by a distance A. And then our final configuration, and the reason why we're doing this is because we want to figure out what the change in potential energy is between our initial and final configurations. We have a separation between the 2-point charges is, sorry, I'm going to call this RA, not just A. The separation is RB. We're also going to assume that only Q2 moved. Imagine that Q1 is like glued down or something. It doesn't really matter which one's allowed to move and which one's not, or if they're both allowed to move. It's just what your reference frame is, which you guys should have learned about in 9A, I think. So the end result of this final minus initial, or of this final and initial configuration business, not end final. Apparently I can't write. The work done on Q2 by the electric field from the first charge. Oh, that's a bummer. The work done on Q2 by the electric field from the first charge would be equal to the negative change of the potential energy of that system. Because if we assume that Q1 doesn't move, then the work done on Q1 is 0. So the change in potential energy is just given by the work done on Q2. So let's compute what is the work done, or the force on Q2. Well, that is the force from Q1. Yeah, that's an E1. That's the electric field caused or created by charge 1, by Q1. So the force on Q2, well, it's just Q1, Q2 divided by the normal stuff. It's just 2-point charges. So it's Q1 times Q2 divided by 4 pi epsilon naught r squared in the r hat direction. This is a completely standard normal force. And so, not normal force, it's completely standard electrostatic force. And so we can compute the work. The work as it goes from its initial to final configuration. I feel like the electric field changes with the distance that charges away. So there's no conductor here. There's just 2 charges. We're done with conductors. That was a method of images thing that we're done with for today. Maybe that helps. Yeah. So big line, it means changing topics. We're just talking about the potential energy of charges now. Just at charges, no conductors involved. So the work as Q2 goes from point A to point B, or a separation distance of RA to separation distance RB, would just be an integral from A to B of F dot dl. And we're going to assume it travels in a straight line. It doesn't actually matter, but we're going to assume that. So the picture here is you have Q2 here, you have Q1 here, assuming that they have different magnitudes just for the sake of this drawing. You have RA, and then maybe at a later time you'd have RB. So the path that it travels is in the radial direction. It's inwards or outwards. And so the force is just, it is what it is. It's Q1, Q2 over 4 pi epsilon naught r squared. And then it's r hat dot dl. Now, just as an aside here, and this is just a line integral thing, the r hat dot dl, because the path is either in the direction, it's either to the left or to the right, depending on how the sign of the charges, we know that r hat dot dl, i.e. the, how do we want to phrase this? The path length vector, or the path vector dl, can be broken up into parts that are in the direction of r hat, in the direction of theta hat and phi hat, for example. But because the object is just moving towards or away from the other charge, dl is just r hat, or it's dr r hat. And so what we get is that r hat dot dl is just dr at the end of the day. That's just because it's moving in the radial direction. And so what we end up with is we can compute the work explicitly. This is just equal to Q1 over times Q2 divided by 4 pi epsilon naught r squared. Or no, the r squared needs to be inside the integral, sorry. Integrate from, God, my handwriting's terrible today, from RA to RB, 1 over r squared dr. And so doing a little bit of simplification, or actually just doing the integral is Q1, Q2 over 4 pi epsilon naught times 1 over RA minus 1 over RB. And so that just is the work done on the second charge. And so the change in potential energy, sorry, I can't talk, is just the negative of that. And so it's just Q1, Q2 over 4 pi epsilon naught. Sorry, that's a 2. Times 1 over RB minus 1 over RA. It's just the negative of the work done. And so this is just the change in the electric potential energy of the system. Now, you may remember from 9a that the change of the potential energy of a system is given by the negative of the work, but sometimes, or in fact always, you can actually write the potential energy itself as some function once you choose a reference point. So we need to do that. To get the potential energy itself, rather than just the change in the potential energy, we need a reference or 0 point. This is just to tell us where's the potential energy 0, and then we can just compute the change in potential energy relative to that point, and that will give us the potential energy according to that reference. And yeah, exactly as Devin suggested, we're going to use an infinite distance, we're going to use infinite distance from our charge as the reference point. And this is a common choice, but it's not the only choice that's ever used. We choose that the potential energy is 0 as r goes to infinity. So it works the same, yeah, it does work the same as gravitational potential energy, precisely. And so the potential energy of a system of charges is just the work. Let me write this out, this is important. The potential energy, so now this is the potential energy, not the change in potential energy. This is just how much potential energy does it have. Potential energy of a system of charges is the work, it's the negative work, required to bring the system together from infinity. So I'll explain in a minute. So let's say that you had a configuration of like 6 charges all arranged in some fancy way, and you wanted to find the potential energy of that system. Well, what you would do is you would imagine that all of those charges were all infinitely far away from each other. They're spread out in the universe, really, really far away. And then you ask, how much work does it take to bring one of them in? Okay, well, that wouldn't take any because it's still infinitely far away from everything. There's no charges yet. Then you ask, how much energy does it take to bring the next one in? Well, that will take there will be some work that's done on that charge as you bring it closer because there's already a charge present. Then you ask about the third one and you bring that one in, and then there's 2 effects. There's electric fields from both of the 2 charges that are already there. Then there's the 4th one that you bring in, and you would add up the total negative work from all of those paths. And then you would add those up, and that would give you the potential energy of the system. And so that's how we're going to define the potential energy of a system of charges. And it's done the same way for gravitational potential energy, or in that case, usually it's called the gravitational binding energy. And so with that reference point for a system of 2 charges, with that reference point at infinity, all we have to do is ask, how much energy does it take to bring in the first charge? 0. How much energy does it take to bring in the second charge? Well, we kind of already computed that. We kind of did that here. So for a system of 2 charges, what we find is that the potential energy, this is a system of 2 charges, as a function of distance between those 2 charges, is equal to the negative work going from infinity to position r. And you can just do that computation now, which is Q1, Q2 over 4 pi epsilon naught r. So it's a really nice formula. It's actually a lot like the Coulomb force formula, except there's only 1 r in the denominator rather than 2. So just as a quick note, if the charges have the same sign, if Q1 and Q2 are both, say, positive, then we would get that the potential energy is positive. So as you bring them closer together, as r gets smaller, the potential energy gets higher. And that's kind of what we expect for 2 things that repel each other. We expect that the potential energy increases if you try to bring them closer to each other, because we know things tend to go towards lower potential energy. Similarly, if they had negative potential energy, you'd find that if you bring them closer to each other, the potential energy gets larger in magnitude, but more negative. So the potential energy decreases. No, we're bringing the charge in from infinity to a position R. And so it checks out that like the signs are correct. If you bring two positive charges close to each other, the potential energy is positive. If you bring two oppositely signed charges close to each other, the potential energy is negative, and that's correct. So just as a quick example that's in the lecture notes, you can use this sort of calculation to find the kinetic energy of a charged particle. And I've given 2 links that point to the online reference that I've been using if you want to check those out at a later date. So what happens if we have multiple point charges? So we already did it for 1 or for 2 point charges. So they would have infinite potential energy if they were overlapping, they would have infinite potential energy. Yes, that's true. And that's actually a problem in classical physics, which is one of the reasons quantum mechanics was made. All that tells you is that this model of physics breaks down at the very, very small scale, right? If 2 electrons got really, really close, something has to go wrong, because otherwise there'd be infinite potential energy, right? Right. So what happens if you have multiple point charges? So just as a summary of what I just mentioned, the potential energy of a system is just the negative of the total work done, or the total work required, or let me use the word done, the total work done that's required to assemble the system. So whenever you think of the potential energy of a system, think of building the system from scratch. You start off with no charges, and then you build the system 1 particle at a time, and you're computing the work done to find the total potential energy. Sorry, it just comes with practice. That's why these are recorded. You can go back and watch it again if you need to. And so the idea is we're just assembling them 1 at a time. So let's take a simple example. Let's say we have a point charge 2, point charge 1, and a point charge 3. So I'm just drawing these lines just to indicate distances. So we'll call this distance R12, this distance R23, and this distance R13, right? So what we're going to do is we're going to try to find the potential energy of the system by assembling it from nothing. So step 1, we're going to imagine that 2 and 3 are infinitely far away. They're not necessarily together, but they're infinitely far away and infinitely far away from each other just as well. So there's just particle 1 or charge 1 just sitting there. It doesn't take any energy to get that first charge in. So the question is how much energy, or how much work rather, is required to get charge 2 in place? By the way, just so then it's clear what we're doing, we're trying to figure out the total potential energy of the system in this configuration. And so we're going to do that computation now, just so you can see an example. So the amount of work that's required to get charge 2 in place is basically this result, right? It just requires the potential energy from 2 charges, because there's only charge 1 and charge 2 yet. Charge 3 is still infinitely far away. It's just now we replace this R here with the distance between the 2 charges. It would be R12. So the potential energy from just bringing U1 and U2, or our Q1 and Q2 together, is just Q1, Q2 divided by 4 pi epsilon naught R12. Okay, step 2, we have to bring in charge 3. I should put a number there. Bring in charge 3. And so how much work does that take? Well, we can compute that. So we know that the electric field, and hence the force, and hence the work done, is additive, right? The work that, in order to bring charge 3 in, you're going to get some amount of work from charge 1, and you're going to get some amount of work from charge 2, and then we can add those together. So the work that's required to bring it in if only charge 1 was there, is that 2 plus 3? That's 2 and 3. Sorry. The amount of work to get charge 3 in place if only charge 1 was there would be Q1, Q3 divided by 4 pi epsilon naught R13. And the amount of work to get charge 3 in place if only charge 2 were there is Q2, Q3 over 4 pi epsilon naught R23. And so the total amount of work that's required to get charge 3 in place when there's both charge 1 and charge 2 present, which I'm calling U1 plus 2 and 3, would be just the sum, Q1, Q3 over 4 pi epsilon naught R13 plus Q2, Q3 over 4 pi epsilon naught R23. And so the total potential energy of the system is just the sum of all of these potential energies, or of all of these works that we computed. So it would just be U is just Q1, Q2 over 4 pi. I'm not going to write them out. You already know, I've already written them all out. So it's U12 plus U13 plus U23. And so if you had more charges, more than 3, you would just account for every pair and add them. And so if you had a 4th charge that you wanted to bring in and put it somewhere, you would have a U14, U24, and U34. So you'll notice as the number of charges increases, the amount of things that you have to calculate increases a lot. There is a general formula for this, but it's not particularly useful. Maybe I'll just give it to you. So this is for n charges. So the n charges are labeled, they're going to be labeled by I and J. I and J. And so the general formula is I equals 1 to n. That should be a lowercase n. I equals, and then I equals 1 to n, and then we also need that I is not equal to j. And so then it would just be Qi, Qj over Rij. So as long as I does not equal j, which is a reasonable thing because the distance between them is 0 and it doesn't take any energy to move a charge near itself. This is exactly what we did up here for n is 3. The only difference that you might be confused by is that there's a 2 here instead of a 4. And that's just because we're double counting, right? You'll find that we would have a Q2, Q3 and a Q3, Q2. And so I just divided the whole thing by, or sorry, I should have an 8 down here. I just divided the whole thing by 2 to indicate to you that, I divided the whole thing by 2 because we're double counting, which sum has j. Oh, sorry. J equals 1 and j not equal to I. That's better, sorry. But that's the basic gist of it. And you'll find that if you do this, you'll get the same answer for 3 charges for n is 3. But don't worry too much about it. It's not particularly important. So there's an example that is, again, that is laid out in the lecture notes. I linked to it. It's just finding the potential energy of a square of charges. So you might want to go give that a shot just to get some practice. The solution is given again, and so it'll be nice to see. So that's all fine and dandy for discrete chunks of charge, but just like how we did for electric field when we were finding the electric field of a number of charges, we eventually wanted to know the electric field of a continuous distribution of charges, like a real object, right? And you might also want to know the potential energy of a continuous distribution of charges. So we're going to do that now. It was a 4. I just divided by 2 since we're double counting. That's all. Because notice that in this formula, there wasn't a 2, 1, or 3, 1. There was just 1, 2, 1, 3, and 2, 3. But if we use this formula, there'd be a 1, 2, and a 2, 1, which are the same, and it would just be double counting. So I just divided by 2 to account for that. So the way that we find the electric potential energy for a continuous distribution of charges is very much the same as what we just did. All we do is we add up the amount of work required to bring an infinitesimal amount of charge from infinity to our continuous distribution and then plop it down. And then we just add up all of those dWs or those du's, i.e. integrate, and that's our end result. So we want to add up the u of dq for a charge. I'm not even going to write words. My explanation made sense, I hope. So let's do an example. This is going to be the simplest example that we can do, although it'll still look challenging. So given a neutral shell with radius capital R, so this is just like a piece of plastic with radius capital R, suppose we want to charge it by moving charges from infinity to the surface. So it's just like a shell of plastic, and we want to charge that shell of plastic. And we're going to assume that we're charging it in a way that's uniformly distributed, so the charge is always uniformly distributed on the surface. So the question then is, what is the potential energy of the assembled configuration if we have total charge Q? So there will be a whole bunch of charges that are close to each other. Like if I'm going to do my best to draw this just really quick. So you'll have a whole bunch of charges distributed. Maybe they're positive, maybe not. And there has to be some energy between them because you have a whole bunch of positive charges that are close to each other, right? And there'd be some on the back too, obviously. Yeah, from infinity to the surface. Yep. So we're bringing charges in from infinity and we're placing them on the surface. And so there has to be some potential energy associated with this configuration of charges because you have a whole bunch of positive charges near each other that don't want to be near each other. And so there's a force present, and hence there would be a potential energy. So what we're going to do is we're going to start calculating. So the thing that we typically do when we do these sorts of continuous problems is we just pick a particular place or a particular configuration and then see what the next bit does. So like with the infinite line of charge, when we wanted to find the electric field, we just said, okay, let's imagine this is our chunk of charge dq. How much does this contribute to the electric field, right? So we're going to do the same thing here. We're going to assume the sphere has some amount of charge already on it, and then we're going to ask how much does adding an infinitesimal chunk of charge to it increase the potential energy by. So at any given time, say when Q charges have already been accumulated, how much du does adding a new charge dq contribute? That's what we're trying to answer, right? We want to know how much does, if you have some amount of charge already, how much does adding just a teensy little tiny baby charge from infinity to the big conglomeration, how much more potential energy does the system gain? And then we're going to integrate all of that, right? So we're going to use Gauss's law for that. So from Gauss's law, and hopefully you remember this, we know that a uniform shell behaves precisely like a point charge, as long as you're outside of it. In fact, a uniform spherical anything, it doesn't have to be a shell, it could be a solid sphere, will behave exactly like a point charge outside of it. Like a point charge at its center. And so basically, adding a new charge dq from infinity to, say, some radius capital R, I'm going to put a dw, so that's the amount of work that this infinitesimal amount of charge does, from infinity to capital R, because that's the radius of the sphere that we're trying to bring it to, would be like bringing a point charge from infinity, imagine that's infinity, to a distance R. That's what we're trying to do. And so you could just do that integral, and it's, in fact, that's just the same answer that we got for two charges. It's just one of those charges is now dq. I'm actually not even going to write it this way. So what we get for that little baby charge is du, that's how much potential energy it adds, is q times dq divided by 4 pi epsilon naught r. So if you go back and look at it for 2 point charges, here it is. It's this, the one on the left, q1, that's the amount of charge that's on the sphere, because we can treat it like a point charge. The dq, well, that's our second charge that we're bringing in from infinity. And then we have a capital R in the denominator because it's a distance capital R from the center, which is where the Gaussian charge is. Erase this, sorry, need that room. So then all we have to do now is just add up all of these little contributions from 0 all the way up to capital R, or sorry, from 0 all the way up to capital Q. We get that the potential energy of a spherical shell is equal to an integral of du over the entire sphere. I'm not even going to put the bound there. And so we can just do this replacement. Now, importantly, usually we don't integrate over q, but here we can, because q is constant, or q isn't constant, sorry. Q is a variable, and dq increases with that variable. And this r in the denominator is a constant. So we can just explicitly do the integral from 0 to capital Q of q dq divided by 4 pi epsilon naught r. And so then it's just an integral with q as the variable. And this becomes q squared over 8 pi epsilon naught r. So that is the electrostatic potential energy of a charged sphere where the charges are uniformly distributed. That just is. That's how much energy it has. And you can think of this kind of as a way of storing energy, right? If you have a whole bunch of charges that are close to each other, that all have the same sign, they don't want to be there. And so you can kind of think of it as keeping them compressed would be holding them in. And if you wanted to use that energy, say convert it to kinetic energy, let them all go. And they will start accelerating away from each other. And so you can get usable work out of that. This is why we consider electrostatic energy, electrostatic potential energy, as the same kind of thing as like gravitational potential energy, because you can convert it from some stored energy, i.e. a rock that's really high up or a bunch of charges that are really close together, to kinetic energy, letting them all go. By the way, note that this is always positive, and that's because for a charged sphere, you have a whole bunch of charges that are all the same sign close to each other. So it makes sense that it's positive. Right. Let's do the next example, which is going to be harder. Oh God, we still have so much to do. So battery stores electrostatic potential energy, kind of, but it stores it in the form of chemical energy. And we can talk about that at a later date. We will get there. So what about the potential energy for a uniformly charged solid sphere? we're going to assume that the total charge is, or that the radius is capital R, the charge is capital Q. It's not quite how electric cars work. It's a little bit more involved than that. But we'll again, by the end of the quarter, you guys will have a basic grasp of circuits, which involves all this stuff. So what we're going to do is we're going to build this sphere, this uniformly charged sphere, by assembling shells of charge. And we already know how to assemble shells. We've kind of already covered that. But we need to figure out how much charge each shell would have when we add it. So let me just jot that down for your notes. So what we're going to do is we're going to bring shells, infinitely large shells, in from infinite radius to some fixed radius, and then we're going to stack the shells on top of each other. So adding each shell is going to contribute to the total energy as if it were a point charge. And the reason for that is because a shell just behaves. How do I want to phrase this? Imagine that you had a sphere of charge, and then you wanted to bring in a whole bunch of charges in from infinitely far away. Let me not have it intersect, right? That would be like bringing in a shell. We want all of these to come in. Well, they're all the same distance from at any given time. They're all the same distance. So we could just instead treat it as if there was one big charge, one big infinitesimal charge that just came in, and it had the total charge equal to the charge on the shell. This is all to say that each shell contributes to the total energy, or it contributes total energy as if it were a point charge. And then the electric field that it will feel, and hence the electrostatic potential energy it will gain, will be from the sphere that's below it. And so this will behave, the sphere that's below it will also behave like a point charge from Gauss's law. So it only sees electric field from the sphere below it, from the partially assembled sphere below it. And that behaves like a point charge. So we're using a lot of behaves like a point charge business, and that's because these problems get hard unless you have a lot of symmetry, which point charges do and spheres do. So now let's actually go through the computation. So first we want to note that, so the charge density, it should be uniformly charged. So the charge density should be the total charge divided by the total volume. The volume of a sphere is 4/3 pi r cubed. So the charge density is 3q over 4 pi r cubed. Check that that's equal to q divided by the volume of the sphere. So now let's go and ask, at some intermediate time, how much extra energy does the shell add? So we're going to suppose the shell has been assembled. Sorry, the sphere has been assembled. It's been assembled to radius little r. So it's not done yet. We want to ask, how much energy does the next shell that adds on to that contribute? So before we can get to that question, we have to answer a slightly easier, or an intermediate question. How much charge would the next shell have? Well, we know that when the charge is, or when the shell is resting on top of the sphere below it, it has some specific charge density. Obviously, the charge density will be smaller when it's like before it comes in, but it'll have some specific charge density. And so if we can find the volume of that shell once it's sitting on top of the sphere, then we can just multiply that volume by the charge, and that will tell us how much total charge that shell had. So the Yeah. So the amount of charge would just be rho times the volume of that shell, right? So it's just rho times, well, what's the volume of a shell that has a radius r and it has thickness dr? Well, it's just the area of the shell, surface area, 4 pi r squared, times the thickness, dr, which is just 3q r squared over capital R cubed dr. I just substituted in what we know rho to be. So that's the charge on the shell, which we're going to treat as a point charge. So now you can imagine that shell, which had that much charge smeared out over it, grab that all and clump it up to a single point and bring that point in from infinity. We also need to know how much charge the sphere has, because that will affect how much energy it gains when it comes in. So I'm going to say that that is the charge at distance when the sphere has a radius r. And again, that's just rho times the volume when the sphere has radius r. The volume of a sphere is 4/3 pi r cubed. So this is just q r cubed divided by capital R cubed, which makes sense. The total charge should be q when the sphere is fully assembled. So if you replaced little r with capital R, you would just get the charge of a sphere of radius r, capital R, would be q. It's a good check. Okay, so we know the charges. We know the charge of the sphere before the shell comes in. We know the charge of the shell. So now we can just, treating them both as point charges, which we're allowed to do for reasons explained earlier, we just compute the amount of energy that the shell adds to the sphere. So it's du, it's the amount of energy that we gain. It's just q times dq divided by 4 pi epsilon naught r. And so now we just substitute. So it's, q over q r cubed over capital R cubed times 3q r squared over r cubed dr over 4 pi epsilon naught r. And now note that r here is a variable. It changes as we assemble the sphere. And so that's why we've written everything in terms of r, because we want to be able to integrate the entire sphere. And so we couldn't have just left everything in terms of q, because the amount of charge changes as we add shells. That's why we had to do that. And that it changes with variable r. And so we can simplify. This is 3q squared over 4 pi epsilon naught r to the 6th, r to the 4th dr. So then we just add them all up. So the total potential energy of the uniform sphere with radius capital R and total charge capital Q is 3q squared over 4 pi epsilon naught r to the 6th times an integral from 0 to capital R. And there's just r to the 4th dr. And so it works out that this is 3q squared over 20 pi epsilon naught capital R. That is the answer. And so now you can go back and actually compare the answer that we got before. This is the potential energy of a spherical shell with charge q and some radius r. We divided by 5 because we did an integral. Compared to the potential energy of a uniform sphere. And you'll note that this is actually larger. 3/20 is bigger than an eighth, right? So the reason why the charges are, why the potential energy is larger is because you can imagine that you take a spherical shell of charge q, and then you start bringing some of those charges towards the center, so that instead of being smeared out just over the surface, they're smeared out throughout the whole thing. Well, that would mean moving positive or like charges closer to each other, which adds up which increases the potential energy. Anastasia, the reason why we multiply the charges is for the same reason that we have here. We're finding the potential energy of two charges or of bringing one charge in to another charge, and the potential energy there is the product of their charges divided by 4 pi epsilon naught times the distance between them. And so the one charge is the partially assembled sphere of radius little r, and the second charge is the shell that's coming in from infinity. And so those are the 2 separate charges. We have this one and this one, and then we multiply them together. Right. So there's another example of a non-uniform sphere that's given in, it's just the same thing, but the charge density is non-uniform. I highly suggest that you guys look at this example because I'm going to give you a problem like this on the homework. So if you understand that example, then you'll fare better on the homework. So this is example 2.1.2. So take a look at that in the textbook, please. It's just doing the same thing, except instead of rho being constant, now rho changes with density as well. All right. Oh God, I still have like 4 pages. Guess I'm not going to get through all of it. All right. So that's how you compute the electrostatic potential energy of a system. But there's something else that you may have heard of, and this is something called the electrostatic potential, or voltage. So that's going to be related to what we just talked about, and I'm going to start talking about it now. Let's talk about the electrostatic potential. So think back to when we first defined the electric field. What we did to define that was we said, okay, imagine that you had some charges somewhere. And then say that you bring a test charge in. What force would it feel if you placed it here, or placed it here, or placed it there? And then we just divided that force by the charge of the test charge. That's a 20. It's just 20. So what we did is we took the force that a test charge would feel, and we divided by the magnitude of that test, or by the size of that test charge. And that gave us a vector at every position in space, which told us what would happen to a charge if you were to place a charge there. So we can do something similar for the electrostatic potential energy. We can ask how much energy would it take to move a test charge from infinity to a particular place. So that's a question that we can reasonably ask. Yeah, well, that's the trouble. So it's a limit, not just 0, right? That's a question we could reasonably ask. And then we can just divide by the magnitude of the test charge. And that will give us just a number, right? Because energy is just a scalar number. So the end result is a number, or a scalar. We'll put not a vector, so that's super important, at every point in space. So basically, you ask, how much energy would it take to bring a test charge from infinitely far away to this place? And then what about this place, and 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 so on. And you do that for every possible position in the universe. And so that will give, and then for each of those positions, you divide the number that you get, the amount of energy, by the magnitude of the test charge, and that will give you just a number that tells you how much energy it would take to bring a charge from infinity to that place. And so that set of numbers, one number is associated at every location in space, that is known as a scalar field. Remember, a scalar is just a number. A vector field was a vector at every position in space. Scalar field is a number, or a scalar, at every position in space. And so we define this as v. We call it v as a function of the position vector r. This is not the distance vector, by the way. It's a position vector now. And this is just the limit of the test charge, as the test charge goes to 0, of the amount of energy, the delta U, that it takes to take the test charge from infinity to the position r. And then we just divide the energy by the magnitude, or by, not the magnitude, by the test charge. Let me move this down so it has a little bit more room to breathe. So this is how we define voltage. That's what this V stands for. So just as a quick note, though, this V is not potential energy. And that's just like how the electric field is not force. Right? The electric field tells you how to get force at any given place, but it isn't force. And similarly, this electrostatic potential V, or this voltage V, isn't potential energy. It just tells you how much energy a thing would have if you moved it to that place. Now, just because you should know this, the units of V is joules per coulomb. Kind of makes sense. Potential energy has units of joules, charge has units of coulombs. But this is often given another name, named after some French guy. It's called the volt. So 1 volt is 1 unit, or it's 1 joule per coulomb. So, and the name that we give this thing, this is called the electrostatic potential, not the electrostatic potential energy, it's just the electrostatic potential. It's very closely related to the electrostatic potential energy, but it's not. They're not the same thing. So just like the electric field had, the electrostatic potential has a superposition property. So given a test charge, Q, the energy required, I thought that was an English class. Sorry, my bad. I need to move this over. The energy required, come on, stop. Sorry, it's moving slowly. The energy required to bring that charge near a collection of charges, that charge near a collection of other charges is, well, delta U would be the test charge's Q. And you're bringing it from infinity to position R. That would be, well, you have charge 1 times Q. So you add this up for all of the chunks, or for all of the separate charges in your collection. So this is going back to, or it's going back to this business where we found the electric potential to bring in 1 additional charge to all of the others. If we brought in 1 additional charge, you'd have to find all of these distances, right? That's what's about to happen. So bringing in a test charge Q to a collection of charges labeled Q1, Q2, Q3, Q4, whatever. This would be Q1 times Q over 4 pi epsilon naught R1. So R1 is, well, I'll explain in a minute, plus Q2 times Q over 4 pi epsilon naught R2 plus ... And you just keep doing with more and more charges. And so the electrostatic potential, we just divide by Q. So it's just Q1 over 4 pi epsilon naught R1 plus Q2 over 4 pi epsilon naught Q. I can't write. R2 plus ... And here, just so you know, R sub I is the distance from the vector R, or from the distance from Qi to the position R. So the charges are somewhere, they're at some position wherever they are. And so this Ri or R1, R2, R3, that's just the distance from Q1 to the position of interest R. There's a lot of R's here, I know. And so this is just the potential energy. You just add up the energy from each of the contributing charges. And so what we find is that the electrostatic potential has the superposition property. So it's just V1 of R. That would be this first term here. plus V2 of R plus ... right? The electrostatic potential superposes. I think that that's the present tense verbification of superposition, I think. So the end result, and this is going to be the end of the lecture, the end result is, given an electrostatic potential, we can find the energy, or we can find the potential energy of a point charge by U is just Q times V of R, where R is the position of the charge. Now, just as a quick aside, this is not the potential energy of the whole system. This is just the potential energy of that single charge. So if you wanted to find the potential energy of the whole system, you would have to figure out how the potential energy changes. You'd have to add up the potential energy from all of the parts in that system. So this is just imagine you have some charge configuration somewhere. What is the potential energy of a single charge elsewhere nearby? i.e., how much energy did you have to use or give it to bring it from infinity to that place? Because if you imagine, you could just have like a whole bunch of charges here. How much energy does a positive charge have if you just put it right there? Well, it has to have some potential energy, because if you hold it there, it won't go anywhere. But the moment you let it go, it'll fly off, right? Find, we can find. Sorry, I dropped word. And so, of course, it has potential energy, and that's the potential energy of just that charge. It's not the potential energy of the system. It's the potential energy of just the charge. If V is joule per charge and Q is charge, so U is work in joules. Wow, units check out well. Yeah, yes. Potential energy is work, as expected. Potential energy was defined as work, right? It's just defined as the negative work. All right, so that's the end of lecture.